Last time, we decided to let the square root of -1 be its own new type of number, hoping it would help us solve Cardon's problem. Doing so is helpful, but finding a solution requires one more insight from our friend, Raphael Bambēli. Bambēli knew that because of the way cubics are shaped, our function had to have a solution that didn't involve the square root of -1. It had to be a plain old regular positive or negative number, as he had seen before. His second big insight here was that for this to be the case, the root of -1 parts of each half of the equation must cancel out when added together. Bambēli used this idea to equate the two parts of the equation to a plus b times the square root of -1 and a minus b times the square root of -1, where a and b are constants that we need to find. To solve, we can first eliminate that annoying cubed root by cubing both sides. The result is a particularly tough system of equations. Bambēli was able to get around this through some clever guessing and checking. If we look at our original equation and test a few integers, we eventually see that 4 is a solution. If we substitute 4 into our new equations, we can solve for a and b and obtain a equals 2 and b equals 1. These values make the two parts of our expression equal to 2 plus the square root of -1 and 2 minus the square root of -1. We can cube these and show that they are in fact equivalent to what we started with. And more importantly, when we add the two parts, as the formula tells us to do, we just get 4, which we know is a solution to our original equation. We have found the solution to Cardon's problem. And what's really interesting is that our problem had nothing to do with the square root of -1, and neither did our answer. However, along the way, we found that by extending our number system to include the square root of -1, we were able to find a solution. And it turns out that extending our number system in this way is helpful in lots and lots of other problems as well. So what did Bambēli do to celebrate after discovering a number so crucial to the future of science and mathematics? He actually did nothing. He discounted his discovery and basically said it was a hack. As ridiculous as that might seem now, Bambēli drew a pretty reasonable conclusion at the time. It just seemed a little too convenient, like a trick devised just to solve problems like this. Squaring numbers had, up until that point, largely been associated with what the operation is named for, squares. A square's area is equal to the length of its side, squared. So positive areas make sense, but what could a negative area be? What even is the square root of -1? Questions like these slowed down the development of imaginary numbers. It turns out there is a much deeper and richer meaning lurking below the surface, but it would take long after Bambēli's death to be revealed.